Good evening. My name is Pankaj Dhote, and I'm working as faculty at Water Resource Department here in IIRS, ISRO Dehradun. So, in continuation with the special course, that is geospatial data set for hydrological modeling. So, in this lecture, we'll talk about the river flow modeling using 1D hydrodynamic models. So this will be the brief outline of this presentation. So it's like, what is hydrodynamic modeling, the applications of hydrodynamic modeling, input data required, and what are the different challenges that are there with when you are going to set up a HD model for a particular river basin or particular river stretch. So we'll be focusing mostly on this input data required and challenges. Then after that, we'll take 3 case studies that we have carried out here. So we'll have the brief discussion on these 3 case studies as well, like flood risk assessment, then integration of HD model with the satellite altimetry data, and then dam release scenario. Okay, now the first question that is here is what is hydrodynamic modeling? Now you might be you might have heard a number of times about hydrological modeling, hydrodynamic modeling. So obviously there is a difference between hydrologic modeling and the hydrodynamic modeling. So in the previous lectures you might have been seen that when we say hydrological modeling, means we want to see the response of a particular catchment for a particular rainfall event. Means what, if I say a particular catchment and when a rainfall occurs, so what will be the response of that catchment that is at a particular gauging site. I want to know for that particular rainfall how much of peak discharge will be generated, or what will be the hydrograph corresponding to that rainfall event. So it's like hydrological modeling means we are interested in linking the rainfall with the runoff for that particular at particular river cross section in that particular basin. Now in this case hydrodynamic modeling, so this is slightly different from the hydrological modeling. Now if you look into this particular diagram, so I have seen this green spots that are you are seeing this green one. Suppose this is the one, and these are the 2 gauging sites where we know the hydrographs, or the suppose in our India Central Water Commission is there, which take cares to monitor the different water level and discharge in the different basins. So now suppose monsoon season is there, and then this particular hydrograph is being monitored at this particular gauging site. Now what I want to know is that suppose this is in the downstream area, there is one particular maybe city or some agriculture land where because of the, if at all this high flood wave comes routes in the downstream direction, what will be the water level and discharge in the downstream side. So what I am aiming in the hydrodynamic modeling is I want to route this particular flood wave, because I know some information that is there in the upstream time, and I want to know the same information in the unknown locations along the rivers. Like I want to know at the red dots that you are seeing. Now here I want to know what is the river water level and the discharge. Here also I want to know what is the river and river water level and the discharge. So the process of knowing the water level and discharge using some information that is there with us, this complete process is obviously we call as the flood routing. But now when I say hydrodynamic modeling, so this the movement of this flood wave right from upstream to downstream can be represented by some physically based models. So one of the example is the Saint-Venant equations, so which is based on the conservation of mass, that is continuity equation, and the conservation of momentum, that is moment equation. Now these are the 2 equations which take care that how flood will move right from upstream to downstream. Now this complete process of providing numerical solution through these partial differential equations, so that we could get the water level, velocity, and discharge in the downstream area. This is nothing but we call as the hydrodynamic modeling. So there are number of packages are available which are efficient to give numerical solution to this partial differential equations, such as you have the open source HCRAS, then you have the Mike 11, then you have the Subek, TwoFlow. So there are number of modeling packages which can provide solution to these partial differential equations, and then that's why we call these different packages as the hydrodynamic models. So so I hope now you have understood that what is hydrodynamic modeling is. It's just nothing but the giving a solution to these two particular equations. Now this is these two equations that you are seeing are in the 1D fashions. However, you could have the represent the flood wave in the 2D fashion always. Shallow water scent variant 2D equations are so available. So for that there are again different models, like that we are not dealing with those kind of models in this particular lectures. So in this lecture we'll be mostly focusing on the 1D scent variant equations. Okay, now now the applications of hydrodynamic modeling, as I said, you understood what is hydrodynamic modeling is just to know the response of the particular flood wave which is there in the upstream, and we want to know what will happen if that flood wave moves in the downstream direction. So we want to know the water level and discharge at every location that are there in the downstream area. So now that area could be the flood prone area where we want to know this information. So now in that case, so this kind of hydrodynamic models can be used for different purposes, like flood inundation mapping for different historical and historical and future extreme flood events, and the flood hazard zonation of different return period discharge magnitudes, flood risk assessment, river embankment overtopping analysis. River embankment means suppose for a particular area we know that every time at a particular cross section is there, or the particular river which is there, where in every monsoon water level overtops to that embankments and leads to the inundation in the low-lying area. So what should be the how we can raise the heights of those embankments so that water level will not exceed. So such kind of different analysis can also be carried out using HD modeling. Then you have the dam break analysis, glacial lake outburst floods, then suppose a landslide dam lake outburst flood also, because of suppose suddenly landslide occurred and it blocks the river flow, and if it blocks the river, so a temporary lake will be created within the river. So if at all because of the that temporary dam that is that got created because of the landslide, if that gets breached, so what will be the impact on the downstream side? So those kind of studies also can be carried out using hydrodynamic modeling. Now, to understand different input data required and what are the different challenges are there when you want to set up a HD model. So we'll try to understand what are the different data sets are required using this particular example of the Tirthan River basin. Now this Tirthan River, if you see, it is there in the Himachal Pradesh, and this Tirthan River is a tributary of Bias River basin. So having a catchment area of around 680 square kilometer. So what we have done is we'll try to set we'll try to set up what are the different steps that are involved when I want to set up a HD model for 9-kilometer stretch of the Tirthan River, which ranges from Dari to Larji. So that we'll try to we'll set up a model, and then we'll feed this HD model with the different return period discharge magnitudes, and we'll try to see the flood extent. Now, this is the generalized methodology that is there with the flood modeling. So what are the different inputs data that is required is the digital elevation model, then surveyed cross sections, land use land cover, observed stage and discharge data. Now once you have the digital elevation model, what you will do is you will perform some hydro processing, and you will you will find out what is the exact river network using the hydro processing. If you have the only one river, like in this case we have taken only one river, so now either you could take help of digital elevation model and you do the hydro processing. Otherwise you can take any high resolution imagery, and from that also you can digitize your river network as well. So this is the second option. And the third option could be you can simply go to into the Google Earth, and you can digitize your river network, and then you can once you digitize that network in the Google Earth, you can convert that into the different fashions, like shape files, like shapefile. This is one of the format. So that format can be again imported into the, suppose you want to import into the HECRAS or Mike 11 or SOPEC. So in any software, HD model software, you can make use of those files. Now this is about the river network. Now second one is the most important input that is required is the cross sections, because cross section is the one who take cares of the what will be the conveyance of the channel, what is the capacity of that channel to hold that water, and then so that is why we say that for HD model the most important parameter is the cross sections. Now the best way that we should get cross sections for the HD model is through the surveyed cross section. But most of the time we don't have surveyed cross sections. Maybe even if we have, so we'll have the limited cross sections. So the other way that we can do is we can extract cross sections from the digital elevation model, and so that as you know, the digital elevation model, most of the space-borne digital elevator, if you use it, for example, if you use the SRTM DM model, DM, or if you use the allospersal DM or tandem XDM or allospersal RTC product, which is again of RTC product of SRTM 30 meter. So if you use any space-borne DMs, so there is no issue from those if you extract the cross section in the floodplain. But if you talk about the channel, they do not represent the bathymetry. They do not represent the water depth within the channel. So if you do not take care of those things, the water, the conveyance that will be represented by your HD model will be inadequate or will be inaccurate. So to remove that the uncertainty that will be created because of just using the digital elevation model, we have to have some kind of surveyed cross section so that you can account for the bathymetry. Now once you ensure that okay, now I can merge both data, digital elevation model and the surveyed cross section, then you can use these hybrid cross sections in your HD model. So this is about the HD model. This is about the cross sections. Now third one is the land use land cover. What kind of land use land cover is there in your floodplain? So it could be agriculture is there, settlement is there, or some kind of different land use land cover. So based on that kind of land use land cover, you have to give the roughness coefficient, that is Manning's N, that you have to give. Suppose I talk about the agriculture or forest, the roughness provided by the such kind of classes will be higher as compared to the channel. If you within the channel, roughness will be less, but if there is southern forest is coming in the floodplain or agriculture is there, the roughness will be more. So to account for those kind of roughness, we have to take care, or we should know what is the kind of land cover is there in that area. Now the other one, the input parameter that we required is the observed stage discharge. Now this stage discharge, again this is required because based on this we for the particular historical event we want to know the response of that, because this boundary condition means what? Now suppose you observed discharge you gave at the upstream side, we want to know the impact of that flood wave in the downstream side. So that is why again we need this observed stage discharge data, which is again important parameter for the simulation, not only for because we want to know the response of that hydrograph, but also we need to know we need the time series of this data set to calibrate and validate your HD model. And what is CalVal, that also we'll try to see in the coming slides. Now again we'll start with the first one, the river network. As I said before, so river network is nothing but the you can generate this river network either using DM hydro processing, you digitize, or you digitize using any high resolution imagery or using any Google Earth. So now in this example of Tirthan river, so this is the Dar is the upstream end and this large is the downstream end. Now these are the two tributaries I have taken, the rain-fed tributaries. So now this is the river network. Then regarding the cross sections, these cross sections I have generated using the in this case I have used the RTC product, that is alloy Persar RTC product, which is the having the resolution of 12.5 meters. So I use this GM to extract the cross sections. So now in this case, this is the typical cross section I have shown it. Now, as we discussed a little bit before, also like digital elevation model. So the we have to very cautious when we use the spaceborne DMs. So like here, the one example that I will try to show you here is the when you download any spaceborne DM from any, like if you download from ASF Alaska Satellite Facility, or if you download DM from the Earth Explorer, you will get the data that that represents the basically terrain model. Means what happens is initially when they generate using if you take any two Cartosat, suppose you have the stereo pairs of any satellite, suppose you take the Cartosat stereo pairs. Now once you generate, after performing all the different steps that are required to generate DM from the stereo pairs, the DM that you generate or the output that you get is nothing but the digital surface model. So it represents the elevation values, do not represent the elevation of the bare earth. It represents the elevation value of the trees. It represents the elevation of the values of the settlements, whatever the area, whatever the different functional classes are there within the area. It represents the top elevation values of those classes. Now, but in any hydrological analysis, what we need is the bare earth model. Like we want to know the elevation values of the bare earth surface, not this elevation at the top of the trees or canopy or settlement. So to do that, there are certain algorithms being developed, and they assume certain elevation height in that particular, suppose settlement is there, trees are there, and they remove those kind of elevation values, and after that they provide you this digital elevation model on the various geoportals. So now while performing this analysis, right from converting DSM, that is digital surface model, to a digital terrain model, certain uncertainty will be there. So we have to ensure that the whatever the team that we are using it will represent the exact geometry of your area of interest. So again, as I said before, like this is how they do the spatial averaging. Like suppose this canopy is there, they will take certain this average, and then this much of elevation they will subtract from the DSM, so that they will get you their DTM, or you can see the digital elevation model as well. So while performing this analysis, some uncertainty will be there, so you have to be very cautious while using the digital elevation model. Now next is once you have the digital elevation model, as I said before, it do not gives you the information of the bathymetry of the channel. So what you can do is, either first thing, it's better if you have the surveyed cross section from any agency, then you can make use of that data set. Otherwise you can go to the field and you can make use of like digital, you can make use of GNSS receivers. You can perform a DGPS survey, and you can collect certain control points. And now here you can see that this is the Trimble DGPS, where we actually went into the field and collected few GCFs. So now this will this DGPS survey will help you to see the how the accuracy of your DM is, and based on that you can you rectify your DM, and later you can use DM in your further analysis. At the same time, this is the total station, so you can take certain survey of the certain cross sections at definite intervals, so that you will have confidence that okay, at this particular cross section this is the depth of channel is there, and accordingly you can edit the cross section that you got from the digital elevation model using this in situ surveyed cross section data, so that you can have the hybrid cross section data set, which is a combination of both a digital elevation model plus surveyed data. Now this is about the cross section. Then the next one is the boundary conditions. As I said before, boundary conditions is nothing but the what is the hydrological information that you give at the open ends of your river stage. Now in this case, I have established data from right from Dari to the Larchi. So these are the two locations. Now at the upstream, when you are running the model for suppose historical events, suppose now in this case I have ran model for the monsoon season of 2005 and 2014. So now in this case in the Dari, so my boundary condition will be the hydrograph of the 2005 or the hydrograph of the 2014, that will be there in the upstream direction, because this is what I want to know. So the impact of this hydrograph of 2014 in the downstream direction, because at Dari I know the what is the discharge, I know what is the stage now, but I don't know what is the discharge and water level in the downstream direction. So that is the aim of HD model, to know discharge water level at each river cross section in the downstream of your the upstream gauging station. So now in this case for Dazi, we'll give the discharge, and you can give the discharge hydrograph, or you can give the water level hydrograph as well as upstream boundary condition. And then you have the rain-fed tributaries. So now for this kind of tributaries, if you have the in situ data set, that is well and good. If you don't have the data set for these tributaries, so then maybe you can perform the drainage area ratio method, or there are certain methods where you can find out the discharge data set, and using those methods you can find out the contribution of these small tributaries, and you can give the again you can give the at these particular locations where these rain-fed tributaries meet with the main river. Now in this case our main river is the Tirthan. So at particular chainage you can give the hydrograph of these particular small tributaries as well. And at the last, that is Largi, this is the downstream end. So now in this case downstream end, you can represent this boundary condition as a rating curve, that is nothing but the plot of discharge against water level. Or if you don't have the information of rating curves at the downstream end, you can give the normal depth as also the boundary condition at the downstream end. So this is about the boundary conditions that we give at the different open ends that are there in the river network. Now in this study I have taken only one river, that is Dari to Largi. So my open ends are just Dari and the Largi, and wherever the river is meeting with the main river. But if you have the multi-river network, so in that case you will have the multiple open ends. Now wherever open end is there, there also you have to give the boundary condition, means you have to feed the HD model with the hydrograph. Now fourth one is the hydrodynamic parameters. As we discussed before, we need to know the resistance of each kind of classes. Based on the what kind of class is there, we have to give the Manning's N value. So we should have sometimes it may happen that the land use land code that you are using in your particular study area is very coarse, so that is not actually giving you the information about the what are the small landscapes are there in your area. So in that case what you can do is you can take help of Google Earth. You can go to the Google Earth and you can find out. Now in this case, if I talk about, I have taken only 9 kilometers of the river. So now this land use land cover is not sufficient to give me the all the information of different kind of land cover use is there in that area. So in that case, I can take help of the any hydrogen imageries, and accordingly I can give the Manning's N, and those Manning's N I can fit into the HD model. So now these are the typical different Manning's N values that you can see. So as I said, like suppose forest is there, agricultural help, it will provide more resistance. But if I talk about the channel, maybe there I will have the resistance. Now, once you feed all those information into the HD model, so how your model is behaving, that to know that, what we do is, suppose my upstream, and in this case it is the Dari is the upstream end. Now at the downstream end, that is the large is there. In this case, I will try to compare how my simulated water level behaves, or simulated water level, or if you say water depth, or simulated discharge behaves with respect to the observed discharge. Now if there is good match between this, or good agreement is there between these two time series, then I can say that okay, my model is working fine, and then I can move ahead. So now in this case, if you just you can see that this is the observed, and then this is the simulated. Now if you can see, there is good match between these two time series. Specifically these peaks are being picked up by HD model. Now I can say that so there is good agreement. And again, if I plot a scatter plot of the simulated depth against the observed depth, this root mean square and RMSE are coming to be RMS is around 0.06, that is 0.06 meter. So this kind of statistics based on this now can help you out that okay, my model is working fine. Now suppose R square is very poor, so now in this case it is more than 0.9. Now it is coming to be 0.4 or 0.5. So I can say that okay, there is certain the parameterization I am doing, or the Manning's N that I am using, because your simulated to match your simulated water level or water depth with the observed depth, you have to change your particular parameter, that is Manning's reference. You keep on changing till there is good match between these two. So now if there is no match, then again you have to go back and you have to change the Manning's N of your channel and the floodplain, or the different classes that you are using. So then you have to come up with the final values of the N, where there is the good match between these two time series. Now once you are okay that okay, these are the particular values of this N for which I am getting good R square, RMSE, or other statistical parameters like NSE, then you can stop your calibration, and then you can say that okay, my model is working fine, and then you can use this HD model results for different applications. The next one is the calibration. Now during the calibration, what we do is we keep on changing Manning's N for so till there is good match between observed and simulated. But when I talk about the validation, now in this case we did validation for 2014. So now when I do the validation, during validation, I do not change the Manning's N. I take any fresh forcings. Now in this case I use the 2014 data set. I use the 2014 data set, but for I can take any different particular extreme flood event, and I can estimate this particular the statistics. And if this is statistics is coming to be accurate, then I can say that okay, this model is giving adequate results not only for the event for which I have calibrated the model, but also for the other events as well. So then later you can use this model for the different applications. So now for this typical, you can see that now this is the result of Mike 11. Then you can see that this is the water surface profile for the complete monsoon season. This is the longitudinal profile. On the x-axis, it is the chainage right from 0 to 2.5 kilometer. The stretch is of around 9 kilometer. Here I have shown it for only 2.5 kilometer. And on the y-axis, you can see this is the water level. So you can see that there is a gradual variation in the water level during this complete monsoon season. So such kind of simulations also you can carry it out. I am showing this here in the Mycelium software, but same facilities available in the open source IIRS model as well. Then now this is the longitudinal profile for water level for 500-year return period. So now again for this you can see that what is the maximum water depth at each cross section you can find out for this particular 500-year return period discharge. So now here I have shown for 500 return period. You can do it this for 100-year, 200, or whatever your area of or whatever your interest is. So such kind of different scenarios can be generated using this HD model. Now same thing again, flood extent in different flood inundation scenarios. Now this is the particular after this is the Bali Chowki area which falls between the Dari and the Larji. These are the two station locations of the Tirthan river. So now you can see that this is for the 500-year return period. At this particular location, this is the main market of the main market road of the Bali Chowki village. So that is getting inundated for the 500 return period, having the depth of around 4.8 to 5.5, 4.8 to 5.4 meter. So such kind of analysis can be done using the HD model. So you can know that if at all in the future, suppose this amount of flood wave is coming from the upstream direction having the magnitude of 500 return period, so which areas may get affected. So such kind of analysis can be done using this HD model scenarios. So now this is again flood extent due to 100-year return period discharge. Then you have this flood extent due to 200-year return period discharge. So you can see that for 100-year return period, so maximum date is reaching up to 6.5. Then as there is increase in the discharge magnitude, the maximum water level is a little bit on a higher side. So now this is about the till now we talked about the considering Tirthan river, and we try to understand what are the different inputs that are required and what are the precautions that we have to take while setting up a HD model. Now we'll try to move ahead with the different case studies. The first one is the flood risk assessment. And now when flood risk assessment, when I say it is nothing but the combination of both three components: so vulnerability, hazard, and the exposure. Now when I say flood hazard rating, now in this case when I want to do the flood hazard or flood hazard map, I want to generate that, I can generate using the HD model. So now this is the typical equation that is there, that is being proposed by Ramston. Then again it is being modified to the Kocha in et al 2016. Now this, if you want to generate this hazard rating, so this is nothing but the function of depth, function of the velocity and the debris factors. Now out of this depth and velocity, you can get it this depth and velocity for, now in this case this is the typical example of the Kullu river. So this depth and velocity you can get it from the HD model. Suppose as I said before, in the previous case studies, we set up a model for the Tirthan river. You can set up model for a Bias river basin also. So now you run that model for a particular return period. Suppose now this is the 100-year return period flood risk mark. So what we have done here is we ran model HD model for a 100-year return period, and we got the depth and then velocity, and based on that we generated the hazard rating. Now once you have this flood hazard rating raster map, So you need to know that you know that hazard and vulnerabilities, these are the two different components. Hazard means that suppose now this is the particular reverse stage. Now in this case, suppose if I go to this. Now suppose I talk about this in this Kallu river. Now if I talk about this particular stage here, it may happen that there is more depth is here, but here suppose the area that is getting inundated in this case, even though depth and extent is more, here hazard will be more, but it may happen that in this area, particular area, there is no settlement. If there is no settlement, means there is no vulnerability, so there is a less vulnerability. So this vulnerability is related to with the what kind of exposure is there and what is the susceptibility or the susceptibility of that particular exposure to sustain against the coming hazard. So to take care of the flood vulnerability, so there are already different depth damage functions are there. So these are now these depth damage functions depends upon the type of exposure that is there within the area which may get inundated. Like suppose settlement is there, then road is there, then agriculture is there. So based on that, you'll have the different depth damage curves. So now you can again this in the depth damage curve. So this depth that you get, so again will be the output of the HD model. So now once you have the depth damage functions, based on these, you can generate the flood vulnerability map. So now once you know the flood hazard already using this equation, vulnerability using this depth damage functions, you can generate the flood risk map. So now once you have the flood risk, it is a combination. It will give you because within the vulnerability, as I said, depth damage function varies with respect to kind of exposure that you are using. So like in this case, settlement vulnerability will be different, for road it will be different. Now after multiplication of all these three components, vulnerability and then flood hazard rasters, so you will get the final combination that we call as the flood risk. So now this flood risk, again you can rescale based on this what is the magnitude of that rescaling factors that you get. You can again divide this complete area into warning, low or moderate or significant. So such kind of to do such kind of analysis of flood risk mapping, you can also make use of the HD model. So this is again one of the example of the application where you can make use of the HD model. Now again we'll move towards the next next application, that is the integration of hydrodynamic modeling and the satellite altimetry data. So now what additional information or what research question that we can answer if we can integrate this altimetry data with the HD model. So now just to brief, if you don't know what altimetry data is the one of the remote sensing data set we using which you can get the water level. You can get the water level at different tracks. And now if you look into this particular figure, you can see, so these are the different tracks that are crossing the Brahmaputra river. So now where suppose this river is crossing, suppose this particular track is crossing at this particular location near Tezpur to the Brahmaputra river. So we can have the water level based on this altimetry data set. Now what additional information or that we can get if we have the water level from this altimetry data, that will try to see in this particular case study. Now all of you know that rating curves, suppose if you visit any central water commission gauging site, so at each in-situ gauging site, they develop a stage discharge relationship. So now once so that relation is nothing but the rating curve. So like once they develop a rating curve, what normally they do is they will keep on monitoring the water level. Now once they know the water level, they can find out what is the discharge for that particular water level using the rating curves. Now for any hydrological study, if I talk about any hydrological model or HD model, the calibration and validation is the important process that we because unless until your calibration validation process is adequate, the results or the outcomes that you'll get will not be reliable. But most of the times what happens is that will not have the much of the gauging stations or even if you have, that will be the gauging stations will be far away. So now for what if I integrate this HD model with the altimetry data and I try to generate the virtual gauging stations just in addition to the in situ gauging station, and so that question that we'll try to see in this particular case study. Now, in this case, you can see this Tezpur and Guwahati. These are the two gauging station, the locations where gauging stations are there. Now, between Tezpur and Guwahati, these are the 4 tracks of the Saral Altica. This is again the one of the altimeter. Saral Altica tracks are passing through this particular passing between the Tezpur and Guwahati. Now, what if I generate the rating curves at this particular locations where this altimeter is crossing this particular river, and if I establish the virtual network, so those information could be used for different hydrological applications. So now in this case, what we have done is we set up the HD model right from Tezpur to Guwahati, and we now, as you know, once you develop the HD model, at each cross section you will get the water level and discharge. So it's like you get the rating curves at all the different cross sections. Now once you know rating curves, whether it is working fine or not, what we can do is at these different cross sections, if we compare the simulated water level of the HD model with the altimetry. So now after this, while comparing that, we can see that in this particular diagram, if you could see this, this is the simulated pattern that we got, flood extent that we got based on the HD model, and the same scenario was generated. This is the photo captured, and you can see that we could visually see that the HD model was able to capture the same flood event that occurred in the downstream of the Cheruteni Dam. At the same time, if the zoomed version of this particular extent map, simulated extent map near the bridge, that also can be seen that a model was able to pick up this visually the event that occurred back in 2018. So such kind of scenarios now can be done using the HD model. So I have shown here 3, but there are a number of applications that can be used, and you can make use of this HD model to answer the different research questions. So okay, this is from my side. We covered what is HD model, then what are the different applications, what are the different input data set required, and we discussed 3 case studies. So thank you.